All right, good morning, everyone. While we get my talk up, I'll tell a joke, which is that when many people say, wow, you're an astronomer, that is so cool. What was the hardest thing about doing your thesis? And I say it was literally waiting for the stars to align. All right, and with that, I would like to introduce the Kepler Giant Planet Search, paper 1, a decade of Kepler planet host radial velocities from the Keck Observatory. Let's start someplace familiar, our own solar system. The giant planets played an important role in planet formation here, as Jen just reminded us. Jupiter and Saturn were responsible for keeping our terrestrial planets small, and Jupiter directed water-bearing comets toward Earth, influencing or perhaps even causing the origin of life. From Doppler surveys, we know that roughly 15% of sun-like stars host Jupiter-like planets. What is not yet understood is whether giant planets help or hinder the growth of Earth-like exoplanets. Many of you are familiar with the NASA Kepler mission, which discovered thousands of planets between the sizes of Mars and Neptune within 1 AU of their host stars. However, this mission was practically blind to Jupiter analogs. This is because planets at the orbital distance of Jupiter have only a 0.1% chance of transiting their star, which is a prerequisite for their detection with Kepler. Also, the duration of the Kepler primary mission, 4 years, the longest running transit survey we've ever had, is quite short compared to the orbital period of Jupiter, which is 11 years. And so a Jupiter analog would transit at most 1 time during the Kepler primary mission. Fortunately, we have other methods for discovering Jupiter analogs. As this audience is very well aware, the radial velocity technique in particular shines at this task. My colleagues and I have spent the past decade gathering precision radial velocities of Kepler's planet-hosting stars to measure the transiting planet masses and also search for Jovian companions. This paper presents the RVs and planet properties, and many follow-up papers are already in preparation. The stars we selected are Kepler planet-hosting main sequence stars that are comparable to the field stars used for blind radial velocity surveys. The figure on the left shows the stellar temperatures and radii of stars in our survey compared to the 30-year Doppler California Legacy Survey recently published in Rosenthal et al. 2021. And the figure on the right is showing the cumulative distribution function of host star metallicities for our survey and theirs, demonstrating that both of these surveys are targeting stars that are a bit more metal rich than a volume limited sample of field stars from Ragavan et al. 2010. For each star, for each of the 63 stars in our survey, we report the number of transiting planets, the number of sub-Saturn, giant, and stellar non-transiting companions, the number of radial velocities collected, the observational baseline in years, the RMS of the RVs, the expected stellar jitter, the significance of any detected trends, and an upper limit on any M sin I companions at 10 AU based on those RV trends or lack thereof. We also report the physical properties for both the transiting planets and non-transiting companions. So let's look at a few of my favorite systems. We don't have time for them all, but if you're interested, I've put the manuscript on my website so you can browse through your favorite systems at your leisure. This is Kepler 68, which has 2 transiting sub-Neptune-sized planets. And we detected Jovian companions at both 1.5 AU and 5.3 AU. The radial velocity time series, which spans from 2010 to 2022, is on the left, with the best fit model shown in blue. The 4 panels on the right show the radial velocities phase folded to each of the planets in our model. There are 2 transiting planets, which are the upper 2 panels, a previously known Jovian planet in the lower left panel, for which we have updated the orbital properties, and a newly discovered Jovian planet in the lower right panel. Both of the Jovians are moderately eccentric. This is Kepler 139, a system with 3 transiting sub-Neptune-sized planets, and we report a Jovian companion at 3.1 AU. The first 3 radial velocities, which are circled in pink in the diagram on the left, were all at the Jovian's up quadrature phase. So if we had not observed the 4th RV, we would have missed this giant planet. This underscores the importance of actually getting appropriate long-term follow-up to discover Jovian analogs. Precision RVs are not enough. Timing is everything, even in comedy. The 4 panels on the right, again, show the RVs phase folded to the periods of each of the planets in our model, including this newly detected Jovian planet in the lower right. This is one of my favorite systems, Kepler 407. It has an ultra short period planet that transits and has a radius of 1.5 Earth radii, making it very likely to have a rocky composition. At the time the system was announced, the giant companion was only detected as a long-term RV trend since a full orbital period had not yet elapsed, and that's indicated by the downward-facing pink arrow. We have now sampled 2 full orbits of the giant planet and greatly refined its properties. It is a massive Jovian, nearly a brown dwarf, with a significantly eccentric orbit at 3.3 AU. The non-transiting companion is a factor of 2,000 more massive than the transiting ultra-short period planet. Our most dramatic discovery was not a planet, but a stellar mass companion to a system of 4 transiting planets in Kepler 1130. The transiting planets are Earth-sized and are all interior to 0.1 AU. Over the last few years, we saw the star approach periastron, producing a change in the RVs of several kilometers per second. The distinctive non-sinusoidal shape of the RV time series allows a precise determination of the companion mass and eccentricity. It is 200 Jupiter masses and highly eccentric. The distance of periastron passage is approximately 4 AU, indicating that the star likely truncated the protoplanetary disk, possibly in a manner that stunted the growth of the 4 transiting planets. Discovering more systems with architectures analogous to Kepler 1130 is critical for building a sample from which to study the effect of eccentric S-type binary stars on the formation and architectures of planetary systems, including small and rocky planets. Here are the architectures of the 63 stars in our survey. Semi-major axis is along the y-axis here. I had to turn the figure sideways to fit it on the slide. And the primary stars are at the top of the slide, off the slide. The systems are ranked by the orbital distance of their innermost known planet. The point sizes correspond to the square root of the planet mass or companion m sin I. Color corresponds to eccentricity, with the most eccentric companions colored bright yellow. The red triangles indicate trends that have not yet inflected in our decade of observations. We can place these planets and stellar companions on a plot of mass versus orbital distance. Systems that contain a Jovian mass or larger body are shown in color, with color corresponding to the mass of the most massive companion detected in the system. The KGPS survey spans 7 orders of magnitude in planet and companion mass, and 4 orders of magnitude in orbital separation. And I'd like to underscore here that as we are in this era of extreme precision RVs, looking for ever smaller and smaller planets, it's important to remember that those planets might cohabit systems with extremely large neighbors. In summary, I've spent the past decade of my life waiting for stars to align, leading the Kepler Giant Planet Search 1. With the help from many patient co-Is, many of whom are here in this room today, so thank you all. We've obtained 2,858 radial velocities of 63 Kepler systems that have transiting sub-Neptune-sized planets, characterizing 185 planets in total. So far, we have discovered 26 non-transiting companions, including 13 Jovian planets, 8 sub-Saturns, 3 stars, and 3 ambiguous trends. We have also updated the masses of 84 transiting planets. This survey will help us determine whether giant planets help or hinder the growth of terrestrial worlds like Earth. Thank you, and I will take questions.
Questions?
Hey, Lauren, awesome talk. So I see that there are 4 trends, it looks like in that plot, or maybe 3 ambiguous ones. So do you have any hope or plans of using direct imaging or astrometry in order to narrow down what those could be, whether planetary or brown dwarf or stellar?
Great question. So certainly continued radial velocity monitoring will help. And in the era where we are turning on lots of new extreme precision RV instruments, please remember that precision is not just an hour-to-hour or night-to-night precision, but for people like me, a decade-to-decade precision. So please make sure that you get enough standard star observations to overlap your baselines with existing instrumentation so people like me can continue to do science. In terms of direct imaging, no, these stars have been searched and there are no obvious stellar companions, but perhaps Gaia will be helpful.
Other questions? Sharon, in the front.
Great talk, Lauren. I'm wondering, among the small stuff, the inner small stuff, what's the fraction of the ones that you have measurements and the ones you don't?
Oh, the fraction for which we have masses?
Yeah, roughly how many have you detected with the device?
Right. So because this was such a large survey, we had a few criteria for which small planets we would even attempt to measure masses. We required at least 20 radial velocities to try to fit the mass of a small transiting planet. And we also required that the planet had to be larger than 1.15 Earth radii. So it had to pass both of those criteria for us to even attempt to fit the mass.
All right, let's thank Lauren one more time.